same embeddings, 3 similarities, 3 totally different rankings. This is the pattern you'll be able to implement by the end, which chooses the similarity and normalization and ranks the top matches. I'm Professor Pi, teaching search and IR with simple Python. Most teams use Elasticsearch for text and vector search because it is durable, scalable, and already fits many pipelines. People embed text with a model and then ask the index for nearest neighbors. That sounds simple, but small choices change results a lot. You can get the same embeddings and see different top matches depending on similarity function, vector scale, and whether you normalize queries or documents. Success means stable rankings that match semantic intent, not surprising swaps caused by magnitude changes. At a high level, Cosine measures angle and cares about direction. Dot product multiplies components and also encodes magnitude. If you want semantic similarity, direction usually matters more than length. But dot product can be useful for hybrid systems where magnitude encodes confidence. The trick is to pick the right similarity and keep scale consistent across documents and queries. We will build a tiny toy in Elasticsearch to show 3 behaviors. You will see a directional match, a magnitude biased match, and how normalizing vectors fixes the bias. This teaches a simple rule you can apply to larger corpora. Now let us set up a small client and a minimal dataset to experiment with. Now we establish a client and define toy vectors. This snippet establishes a local connection to Elasticsearch using the Elasticsearch Python client and prepares a minimal dataset. The variable ix holds the index name we will reuse. The list docs contains 2 documents, a vector near our query direction, and a larger magnitude vector along the x-axis to expose dot product bias. The list Q is a query vector we will reuse for searches. The client call ESPing checks that the server is reachable and returns a boolean. If ping is false, your instance is not responding on localhost. Seeing ping equals true confirms the client is ready and our toy vectors are set for the next steps. Next, we create the index and write the 2 documents. This example creates an index in Elasticsearch with a dense vector field named v using es.indices create. The mappings block declares 3 dimensions and a keyword t for labels. Next, es.index inserts document A followed by document C, which includes refresh wait for, so the changes are visible immediately without a separate refresh call. The esCount call verifies the number of indexed documents. If you increase dims, vectors must match that size. Mismatches will be rejected. Keeping mappings explicit prevents silent errors later when we switch similarity functions. The printed docs equals 2 confirms both vectors are stored and searchable via scripts. Now we run a cosine similarity search to see direction-only behavior. This code runs an Elasticsearch search using script score to compute cosine similarity between the query vector Q and the stored field v. The query uses match all, so every document is scored by the cosine similarity function, and plus 1.0 shifts scores to a positive range for readability. The variable res holds the response, and h is the top hit from res hits. Because cosine normalizes direction, the near direction vector should rank first, even versus a much larger magnitude vector. If you increase size, you'll retrieve more candidates sorted by this score. The printed top ID and score show cosine favors the directional match, which is what we want. Next, we repeat the same query, but use raw dot product. This snippet repeats the Elasticsearch script score search, but swaps cosine similarity for dot product. The query again scores all documents and returns only the top result. Because dot product multiplies component-wise without normalizing, the bigger magnitude vector C can dominate even if its direction is a poorer semantic match. The variable res captures the response, and H selects the first hit for printing. This illustrates why raw dot product often makes hybrid retrieval unstable. Slight embedding scale changes shift ranking. If you compare different model checkpoints, this bias can worsen. The printed top IDC and its higher score confirm magnitude bias is driving the result. Now we fix the bias by normalizing and using KNN with dot product similarity. This code defines a small unit normalization lambda u and creates a new Elasticsearch index configured for KNN with dot product similarity. The mapping indexes field v, so HNSW can run. It indexes the normalized vector for document A using es.index. In practice, you should normalize every document and also normalize the query. The KNN parameter in es.search runs approximate nearest neighbor using the normalized query. Increasing num candidates may slightly improve accuracy at a small latency cost. Increasing K returns more neighbors. The printed ID shows the normalized dot product now mirrors cosine behavior, delivering a stable, directionally correct top result for KNN. This toy maps directly to a real system. In production, normalize embeddings at index time and normalize queries. Use HNSW for scale and tune num candidates for recall. If you rely on raw dot product, understand what embedding magnitude encodes so you do not accidentally reward length over meaning. Recap: it is about similarity, choice, and scale. Use cosine when direction matters. Use dot product only when magnitude encodes useful signal and you control scale. Caveat: inconsistent embedding magnitudes produce unstable rankings. Next step: normalize all document and query embeddings, and then tune the KNN num candidates parameter to trade recall for latency on your full corpus. If practical IR helps, subscribe and watch the IR videos.